So how much radiation does a human actually emit, assuming we're scantily clad so the radiation can actually escape? Is it enough to cool us down when we're exercising to get rid of a couple of 100 watts? Well, we can calculate it. As we saw, humans are effectively very close to being pure black bodies at the mid-infrared wavelengths where we radiate at. So the total amount of radiation is just given by a power equals the area of a human, which is typically between 1.6 and 1.9 square meters. So let's call it 2 square meters. So van Boltzmann constant times t to the fourth. So let's say we're at 35 C, so that's 273 plus 35 in Kelvin. And if we calculate all that, the power comes out as about 1000 watts, which is a lot. I mean, when we even hard exercise, running a marathon, nearly burning maybe 400 watts, so we're losing far more heat than that. It sounds like it should be easy to keep cool. In fact, the trouble will be keeping warm. If we're losing 1000 watts and only generating a few hundred, we should freeze to death. We need some thick clothes on, even when exercising hard. So what's wrong here? Well, this is wrong, and the reason is that we've factored in the radiation coming out, but we haven't factored out the radiation coming in. This is how much we'd lose if we were surrounded by nothing in deep interstellar space. However, in reality, we're normally surrounded by the atmosphere, by building walls, by the ground, most of which is at a fairly high temperature. Most of it is radiating itself. So we've got radiation from everything around us, the walls, the chair, the furniture, other people, coming in. Now, in principle, we could work this out by calculating the power emitted from, say, the floor, from the walls, and then using the inverse square law to calculate how much that hits us, and then do the balance, which would be complicated and tedious. But there is a shortcut. Let's just assume that we're completely surrounded by some things at some outside temperature, let's call it, I don't know, T, outside. It's all around us. Now, that won't really be the case. For outdoors, there'll be the sky and the ground, which should be at different temperatures. But actually, at these infrared wavelengths, the sky is pretty opaque due to all the water vapor and carbon dioxide in it. So it's actually glowing, so it's not too bad an approximation. Now, if the temperature of us and the outside was the same, then we're in thermal equilibrium. The heat radiation in and heat radiation out would have to balance. Remember that for a black body, we're talking about the jiggling in the atoms producing the field, and they're in equilibrium with each other. So if the wall and the body are at the same temperature, they're all in equilibrium with the radiation field. So if T in equals T out, then everything will balance. What that means is if you want to calculate how much heat we receive from our environment, assuming the complete environment is at the same temperature, that's got to be the same amount that we would radiate if we were at that temperature. So that's the trick. So the net power, in this assumption that we are a black body, everything around us is a black body, is going to be A sigma T us to the fourth minus A sigma T outside to the fourth. So if we're 36 degrees and we're running around in a 36-degree day and all the walls and the ground and the clouds over us are all at 36 degrees, then we can't lose any heat from radiation at all. Or to be precise, we are losing heat, but it's being exactly compensated by the amount of heat we're receiving from everything else. So this only works if it's cooler outside. If the environment T outside is 20 degrees centigrade, then the total power comes out as about 184 watts. Whereas if the temperature outside was 0 degrees C, you're running around in the nude on a freezing cold day, then the net power is about 391 watts. So what's this telling us? It's telling us that if it's cold outside, then running around in the nude so you can radiate on a 20-degree day, you can get rid of most of your heat, and if it's a freezing day, you can get rid of most of your heat. So overheating is not going to be a problem for athletes running around in the nude on freezing cold days. which I guess more or less is what we'd expect, not that I've tried it. In fact, it's telling us there's a reverse problem. Remember that 400 watts is what an athlete working really strenuously radiates. A normal person just sitting around doing not much is radiating about 100 watts. So if you're sitting around in the nude on a freezing cold day, radiating 100 watts, using up 100 watts, but radiating 391 watts, you're going to start cooling down. You're going to get hypothermia and die. So in fact, at cold temperatures, if you're not energetically exercising, it's not heating up that's the problem, it's cooling down that's the problem. And so what you can do is, for example, have clothes on. Some clothes actually have mirrors on the inside, mirror-coated inside. My coat has this, silvered inside, so the radiation that goes from your body to the coat is reflected back in to make it not a black body. But the main purpose of the clothes is that their outside surface is much colder than you are. So while your body may be at 36 degrees here, the outside might only be at 10 degrees. And so while you're still radiating, you're radiating much less. You're radiating as a 10-degree black body from the outside of your clothes and not as a 36-degree black body. So that cuts down the radiation losses quite dramatically. So in freezing weather, if you're not being energetic, clothes are a good idea.